Hey class, we're going to talk about analyzing rational functions today. This is the first day of this unit, and so we're going to just look at some different things about rational functions, and we're going to spend a couple days on this topic. So what we're going to look at today is with a rational function, meaning some type of function that's it's being divided. We've got a polynomial on top, polynomial on the bottom. We're going to be able to identify points of discontinuity, so points that kind of mess our function up. We're going to be able to decide which of those discontinuities are holes, be able to find x and y intercepts, and then find horizontal asymptotes for rational functions. So the first thing we're going to look at is discontinuities. We're going to kind of briefly go over each topic, and then I'm going to do 2 example problems for you so you can see how to do this. So a discontinuity is going to be any place like outside of the domain. So discontinuities happen at numbers, not in the domain. And when we're talking about a rational function, these are going to be places where the denominator is 0. That's going to be a number that's going to be outside of our domain. That's going to mess our function up. It's going to cause a discontinuity. It might cause a asymptote, a vertical asymptote. It might cause a hole. It typically won't cause a jump. Jumps are usually with piecewise functions. But it's going to either create a hole or it's going to create a infinite discontinuity or a vertical asymptote. So we'll have to decide. When I look at one of these, I'll show you when it's one versus when it's the other. So based on the discontinuity, it's either going to be a hole or it's going to be a vertical asymptote. When it's a hole or a removable discontinuity is whenever your factors cancel. So it's going to be a hole if the factors cancel. And it's going to be in vertical asymptote if they don't cancel. This will make more sense whenever we do an example problem. The next thing we're going to look at is how to find a horizontal asymptote. So for a horizontal asymptote, the word asymptote, you've probably heard that it means that the function doesn't touch it. With a horizontal asymptote, sometimes it will get crossed. It's just that as the numbers get large, it approaches that asymptote. So it might cross it, but as it gets bigger, it's getting close to it. So with a horizontal asymptote, for instance, like if this was my horizontal asymptote, my function, as it gets large, might bounce around across it, but it's going to get closer and closer. So it might cross it, but it just gets very, very close to that number. That's going to be our horizontal asymptote. With horizontal asymptotes in a rational function, there's 3 cases, and it depends on the powers of the numerator and denominator. So the first case is if the numerator has a larger power than the denominator, then there's no horizontal asymptote. So that's the first one. So if the numerator's got a bigger power than the denominator, as it gets bigger, the whole thing is going to get bigger. And we'll look at an example of that in a second. The second case is if the powers match. So if the power of the numerator and denominator match, it's the coefficient of the leading terms. So if the power of the numerator and denominator match, it's the leading coefficients divided. So far we've covered if the numerator has a larger power, if they have the same power, and the last one is if the denominator has a larger power. So if the denominator has a larger power than the numerator, then it has a horizontal asymptote at y equals 0. Alright, this is all a bunch of information. It'll make more sense once we apply it here in just a second. The last thing is stuff that you've worked a bunch with, which would be x-intercepts and y-intercepts. So for an x-intercept, this is going to be where y is 0, and the y-intercept is where x is 0. Okay, remember, you can pause this video at any time to kind of jot this information down, and then we're going to run through 2 example problems that's going to make this all much more concrete. We're going to find discontinuities, determine whether they're holes or asymptotes. We'll look at horizontal asymptotes, depending on which one of these cases it falls under, and then we're going to look at finding your x and y intercepts. I'm going to switch pages here and jot down an example problem. So we have a function, f of x, and let's see, x cubed minus 16x over negative 4x squared plus 4x. And we're going to find all of the stuff we talked about on the front. So discontinuities, holes, horizontal asymptotes, and then our x and y intercepts. First thing we need to do is we need to factor the top and the bottom, because we're going to need to kind of see if factors cancel and help us analyze this function. So to factor the top, it shares an x, so it has a GCF of x, and it's left with x minus 16, x squared minus 16. And on the bottom, I can factor out a GCF of, let's go ahead and get the negative as well, so negative 4x, and we're left with x minus 1. Okay. I don't want to cancel anything yet. I'm going to kind of keep everything as I go. So I can go ahead and factor that as well. So x squared minus 16 will factor as x plus 4 times x minus 4. That's the difference of squares. On the bottom, I have negative 4x times x minus 1. So the only factors that I see that cancel would be these x's would cancel. So the first thing we're going to look at is discontinuities. And discontinuities happen where the denominator is 0. So I have discontinuities at, well, 0 would make the denominator 0, or 1. So at 0 and 1. Now if it's going to be a hole, which is the next thing we need to look at, it's always going to happen at one of these. So, or maybe neither one of them, but if it's going to happen, it's happening at one of these values. And holes are the ones that cancel. So the one that's canceling, the x and the x, was the 0, and so this has a hole when x is 0. The reason that works is, as you approach 0, these are going to keep canceling every single time, and so we kind of get the what's left over. And so there's just a hole right there when it's 0, because we can't have it, and then they keep canceling after that. Okay? So we'll talk about that more next week. But if they cancel, it's a removable discontinuity, which is a hole. The next is the horizontal asymptote. And this, there will only be one, if there is one. And this is based off of, well, what does the function approach as x gets large? So I kind of like to pick a very large number and plug it in and see what happens. So we could check something like, let's see, it's 100,000. So I'll have to go grab, oh, nope, I got one right here. Grab a calculator. And I'm going to plug 100,000 in. You could plug it into either one of these, doesn't matter. I'll plug it into my original. So I'll do 100,000 cubed minus 16 times 100,000. Well, there's the top, divided by negative 4 times 100,000 squared plus 4 times 100,000. and I get a very large negative number. So as this gets bigger, as x's get very large, our equation is getting extremely small, like headed towards negative infinity. If you checked maybe a bigger number, you could see, well, is it getting even smaller? So if you checked, like, let's tack on another 0 and check a million. So if I scrolled up and I insert another 0 here, and insert another 0 there, a huge number, divided by -4 times, let's see, a million squared plus 4 times 1, 2, 3, 4, 5, 6, a million. And that's a even larger negative number. So our horizontal asymptote, there isn't one. And if you look at the shortcuts on the front, if the power of the top is bigger than the bottom, so we have a power of 3 over a power of 2, then there's going to be no horizontal asymptote. The reason is this leading thing has the biggest power, has the most influence over the function. So since this has a bigger power, it's going to get larger much faster than the bottom does. So this is going to get large very, very quick, where this doesn't, it gets large fast, but not as fast as the top. So it's going to go off to infinity. So horizontal asymptote is going to be none. Next, we're going to look at our x-intercepts, which our x-intercepts are where the function is 0, which is where y is 0. So if this was 0, so I'll use my factored form. 0 equals x times x plus 4, x minus 4, over -4x times x minus 1. Now this looks like a lot, but if this fraction was going to be 0, the top has to be 0. The bottom can be whatever you want it to be, but the top has to be 0. Well, the bottom can't be 0, but the top has to be 0 in order for this to be equal to 0. So we're really ignoring the bottom. And the numbers that make this top 0 are 0, -4, and 4. Now, the one of these that's a problem is 0, because it would also make the denominator 0. So we only have two x-intercepts, -4 and 4. The last one's the y-intercept. There's only going to be one of these. We only have one y-intercept. And this is where x is 0. So we just take our original function and plug in 0. We end up with an issue, because if you do that, plug in 0, we get 0 cubed minus 16 times 0 over -4 times 0 squared plus 4 times 0. Anyways, f of 0 is 0 over 0, which is undefined, so there's none. Alright, let's look at another example. So example 2. We're going to do f of x equals x squared minus 9 over 3x squared minus 3x minus 36. The first step here is going to be to factor it so that we can get a better understanding of these different properties. So the top factors as x plus 3 times x minus 3. The first thing to do on the bottom is to factor out a 3. We're left with x squared minus x minus 12. I'm going to continue to factor by factoring this. So I've got on top x plus 3 times x minus 3. And on bottom, this is going to factor as x minus 4 times x plus 3. Alright, so let's go through and look at each one. So the first thing is discontinuities. Discontinuities happen at any point that makes the denominator 0. Any number that's outside of our domain. So these are the numbers that make the denominator 0. It's going to be 4 and -3. To determine if one of those is a whole, if it's going to be a whole, it's going to cancel top and bottom. It's going to have a factor on the top and the bottom. So we have a whole at x equals -3, because that factor cancels top and bottom. The next thing is the horizontal asymptote, and this is the one that has the 3 cases, or we can also think through it. So the horizontal asymptote, if I look at my original function, I have the same power on the top as I do on the bottom. So that means that the top or bottom's not going to get faster a lot quicker than the other one. They both have the same power. So if you follow the shortcut on the front, you just take your leading coefficients and divide them. So this is going to have a horizontal asymptote at y equals 1/3. To show that this actually happens, I'm going to pick a large number. And why don't we do like 100,000 like we did on the other side. And I'm going to plug it into the original and see what happens. Or you could plug it into the factored, it doesn't matter. So on top, I've got 100,000 squared minus 9 divided by 3 times 100,000 squared minus 3 times 100,000 minus 36. It's minus 36. And I get 0.333333. That is awfully close to this guy. And if you pick a bigger number, you're probably going to get even closer. So if I put an extra 0 there and an extra 0 here, now I'm using a million. Look at that. We're super, super close to 1/3. So that's a way to, instead of memorizing the rules, kind of know the rules, but then use your calculator to double check. Okay. So this has a horizontal asymptote, it's 1/3. As x gets bigger, it's going to approach this value, 1/3. All right, the last thing we have to find are the intercepts. So the x-intercepts happen when the function is equal to 0. Now, this would be like 0 equals x plus 3 over x minus 3 over 3, x minus 4, x plus 3. So anything that makes the denominator 0, or anything that makes the top 0 but doesn't mess up the denominator. So these would mess up, so we just want to pick this one. So this has an x-intercept at 3. For the y-intercept, this is where x is 0. So I like to just take the original function and plug in 0. So 0 squared minus 9 over 3 times 0 squared minus 3 times 0 minus 36. And this simplifies to negative 9 over negative 36. And if we simplify that fraction, that is a 1/4. So it's going to have a y-intercept of 1/4. All right, hope this kind of makes sense. The only one we didn't go over is if the horizontal asymptote's at 0, and that's just going to happen if the degree of the bottom, the power of the bottom here, is bigger than the top. We'll go back over this on, what would that be, Monday? Clear up stuff, and we'll also start graphing these a little bit. So hope you guys have a great day. Sorry the video is a little long, but I wanted to make sure to hit enough examples that you would be able to continue to work on your homework. So thanks for listening, and I hope you guys have a great rest of your day.